Welcome back to the Prompt Engineering series. This episode goes deep on one of the most important techniques in applied LLM work, chain of thought prompting. By the end, you'll understand what it is, why it works at the token level, its main variants, where it breaks down, and the interview questions you'll be asked about it. Let's get into it. Here's the roadmap. First, the core problem chain of thought solves. Then a precise definition and a concrete example. We'll cover why it works mechanically, look at real benchmark data, and walk through the major variants: zero shot, few shot, and self-consistency. Then the part most tutorials skip: the edge cases and failure modes. And we'll finish with interview questions and answers. Start with the problem. A large language model generates text one token at a time, each token conditioned on the ones before it. When you ask for the answer to a multi-step problem directly, you force the model to compress all of that reasoning into a single forward pass. For anything involving arithmetic, logic, or several dependent steps, that compression fails, and you get a confident, wrong answer. Chain of thought prompting changes the target. Instead of mapping the input straight to an answer, you prompt the model to produce the intermediate reasoning steps first, and only then the final answer. Input to reasoning to output. This was formalized by Wei and colleagues at Google in 2022. The reasoning trace is not decoration, it is the mechanism. Here's the canonical example. Ask: a cafeteria had 23 apples, used 20, then bought 6 more. How many now? Prompted for a direct answer. Weaker setups often blurt 27. With chain of thought, the model writes: start with 23, minus 20 is 3, plus 6 is 9. The answer is 9. Same model, same question. The only change is that we let it think on paper. Why does this work? 3 reasons. 1. Each generated token becomes context for the next, so the reasoning trace acts as an external scratchpad the model reads back as it goes. 2. It's test time compute. More tokens means more effective computation applied to the problem. 3. Decomposition. A hard problem becomes a sequence of easy substeps, each within the model's reliable range. You're not making the model smarter, you're giving it room to work. And the data is dramatic. On GSM-8K, a benchmark of grade school math word problems, standard prompting on a 540 billion parameter model scored about 18%. With chain of thought, the same model jumped to roughly 57%, more than triple, with no retraining, just a different prompt. But here's a critical caveat. This is an emergent ability. Plot accuracy against model size, and you see it. For small models, chain of thought gives little or no benefit, and can even hurt. The gains appear only past a certain scale, roughly the 100 billion parameter range in the original work. Chain of thought is not a universal switch. It's a capability that unlocks with scale. There are several ways to invoke it. The simplest is zero-shot chain of thought, from Kojima and colleagues. You add one line. Let's think step by step. No examples needed. That single phrase reliably triggers a reasoning trace and was shown to massively improve zero-shot accuracy on reasoning tasks. It is the highest leverage 7 words in prompting. More powerful is few-shot chain of thought, the original method. You provide a handful of worked examples, each showing the full reasoning, not just the answer. The model imitates that pattern of reasoning on your new problem. It costs more tokens, but for domain-specific or unusual formats. Demonstrating the reasoning style outperforms just asking for it. Next, self-consistency, from Wang and colleagues. Instead of generating one chain, you sample several independent reasoning paths at a non-zero temperature, then take a majority vote on the final answers. Different chains may make different errors, but correct reasoning tends to converge on the same result. This consistently beats a single greedy chain at the cost of multiple model calls. 2 advanced extensions. Least to most prompting explicitly decomposes a problem into ordered subproblems and solves them in sequence, feeding each answer forward. Tree of Thoughts goes further. The model explores multiple branches of reasoning, evaluates them, and can backtrack, like a search over thoughts. Both trade more compute for harder problems. Let's apply it to something less trivial. A train leaves at 2:50 p.m. and the journey takes 95 minutes. What time does it arrive? Direct answers often fumble the hour rollover. Chain of thought. 95 minutes is 1 hour 35. 250 plus 1 hour is 350. Plus 35 minutes crosses the hour to 4:25 p.m. Explicitly handling the rollover, the edge case, is exactly where the steps earn their keep. Now the part tutorials skip, when not to use it. First, simple, single-step tasks. For a factual lookup or a basic classification, Chain of Thought adds tokens, latency, and cost for zero accuracy gain, and can even nudge the model to overthink a trivial answer. If the task isn't multi-step, skip it. Second, small models. The benefit is emergent, remember. On a small or heavily quantized model, forcing a reasoning trace can degrade accuracy and just burn your token budget. Match the technique to the model scale. Third, and most important for production, faithfulness. The reasoning the model writes does not necessarily reflect the computation that produced its answer. A model can generate a plausible-looking chain that rationalizes a conclusion it reached some other way. So never treat a chain of thought as a true audit trail or an explanation you can fully trust. It's a performance technique, not a guarantee of transparency. There is always a trade-off. Chain of thought multiplies output tokens, often 3 to 10 times, which directly raises cost and latency, and self-consistency multiplies that again by the number of samples. In a real product, you budget for this. Reserve heavy reasoning for the queries that need it, and route simple queries to a direct path. A 2026 update. Modern reasoning models, the O series and similar, are trained with reinforcement learning to perform chain of thought internally before answering. With these, you often don't prompt for steps explicitly. The model already reasons under the hood. But understanding chain of thought stays foundational. It is the principle these models are built on, and you still control its depth and its cost. Quick interview prep. The questions you'll actually get. What is chain of thought? Eliciting intermediate reasoning steps before the answer. Why does it help? More test time compute, plus decomposition into reliable substeps. Zero-shot trigger? Let's think step by step. What is self-consistency? Sample multiple chains and majority vote. Biggest limitation? The reasoning isn't guaranteed to be faithful, plus added cost, and it's emergent only at scale. To recap, chain of thought makes a model reason in steps, which works through scratchpad context, more test time compute, and decomposition, but only at scale, at real token cost, and without guaranteed faithfulness. Master when to use it and when not to, and you're ahead of most practitioners. If this was useful, subscribe to @Techfluencer Eval. Next episode, we build on this with retrieval augmented generation. See you there.